Greetings, everyone. Essentially, my analytical design presentation will focus on the segmentation of spines and dendrites through machine learning. So then, as I mentioned in my past experimental presentation, this would have been my overall analysis pipeline. But for this presentation, I'll mainly focus on the region of interest maps of dendrites and spines through the generation of binarized mass of each of those through using a machine learning algorithm. And essentially, this is what it should look like. So essentially, when by feeding a pyramidal tract neuron, it should be able to extract binarized dendrite data in separation of binarized spine data. So why using machine learning segmentation is necessary to separate dendrites and spines is that if you chose to binarize based off a signal threshold, this first wouldn't work because brightness alone, as you can see in this image, can't really be used to distinguish dendrites and spines because as we see, they have around the same similar brightness levels. And then in addition, by implementing a threshold on each pixel individually, you ignore the spatial relationship among neighboring pixels, which is really important in order to assess whether that region is a dendrite or a spine. And then most importantly, it's just very poor at generalizing any image you use because as we can see that among these three images shown here, there's a variation in brightness level in dendrite regions, but in also spine regions. And so in addition, manually selecting pixels as either a dendrite or spine can be used to achieve ground truth, but this isn't optimal because it is very time consuming for data sets that could potentially be 1,000 by 1,000 pixels. And then in addition, the judgment of whether a pixel is a dendrite, spine, or background varies differently from people to people. And then alluding to this reason, very weak spine or dendrite signal can be easily overlooked as background signal as shown here. So my machine learning segmentation pipeline will essentially start with extracting 31 two-photon images with various imaging parameters from this open framework, and then that will be fed into a bag decision tree classifier that I've made myself with MATLAB. And from this, I aim to achieve a binarized dendrite mask and binarized spine mask dataset as shown here. So then how my MATLAB code works is essentially I'll start by processing the training data that I've extracted from that open framework. And so to start each pixel of training set images, we'll store the intensity value, a local mean of pixel intensity in a 3x3 region of neighboring pixels, same thing as that the local mean, but in a 5x5 region. And then also I'll get the standard deviation, but in a 3x3 region among neighboring pixels for each pixel. And then for each pixel, I'll finally get the gradient magnitude, which is essentially shows how much the brightness changes among neighboring pixels. So then once I've done that, I'll then label each pixel as 0 with background, 1 with dendrite, and 2 with spine, based off ground truth images also extracted from that framework. So then once I've done that, I'll feed that then into my algorithm, which I'll explain more detail in later slides. But essentially, it's going to be my algorithm is a bag decision tree that contains 150 decision trees that contain a random subset of training pixels. And then after this has been done, I'll then use a validation image. And same thing like the training set data, I'll extract features from each pixel of the validation image, like those in the training set data. And then 150 trees mentioned in the bag decision tree will then vote on each pixel's label. So then now in this slide, I'll essentially explain what a bag decision tree does. So I'll first explain what one decision tree does. So essentially what it does is that it takes in the training data pixels with each of the features as I mentioned previously, and then it'll ask a question that essentially compares a pixel feature to a threshold. So for instance, it can first start with asking, is the intensity more than 0.035? And as it asks questions, it'll then propagate down to another question. So for instance, if the answer was yes, it can then ask, is the gradient more than 0.04? And then as it keeps asking questions, it'll propagate down the tree until it reaches a node, and then that'll just be the final conclusion of whether it is either background, dendrite, or spine. So what my code does for each decision tree is that MATLAB will create 100 questions during training, and then with the collection of each tree will train a random subset of training pixels, and because of this, each tree will have slightly different questions and thresholds. So then once this has been done for a new validation pixels, all 150 trees in this algorithm will then vote and determine the final label based off the majority vote. So then here I'll talk about the performance of my algorithm. So essentially, to start with dendrites, it was, as we can see here, comparison to a ground truth, it was able to detect 98.1% of true dendrite signal and only missed 1.9%. And in addition to this, only 0.57% of background signal from the ground truth was mistaken as dendrite. But unfortunately for spine prediction, it's not so good because as you can see from here and here, only 5.92% of true spine pixels were captured, meaning that 94.08% of spine pixels in the ground truth were missed, but the false detection was nearly the same as dendrite, as only 0.48% of background pixels was mistaken as spines. And the time for this it took to train was 13.83 seconds. So now moving on to the discussion. So essentially what my results show is that dendrite segmentation worked very well because I believe it was easier to identify pixel-based features such as intensity, mean, and gradient with large and smooth structures such as dendrites. But unfortunately, because spines are very small, irregular, and have a low contrast, it makes them difficult to capture with local features implemented from my vector, meaning that as a result, this is probably why spine segmentation performed very poorly. So as you can see, the limitations of using this bag decision tree algorithm is that because it only uses local pixel features, it cannot learn the shape patterns because there's no spatial context. And then in addition, it also struggles with small and noisy objects because each pixel is treated independently. So the future step would be to use a convolutional neural network because this does a much better job at learning the spatial patterns without having to isolate each pixel. It can automatically also extract more features such as edges, textures, and shapes. but it's also able to detect small structures like spines far better than the original decision tree since it is more robust to noise, low contrast, and image variability. And then what this group did is that by feeding an MRI images into their convolutional neural network, they were able to segment brain tumors, meaning that and showing that CNNs just excel far better at biomedical segmentation than using just a decision tree. So essentially how these masks will be used is at the start, I'll multiply the dendrite binary mass with the NADH lifetime in order just to extract the NADH lifetimes of interest. And then with the spine binary mass, that'll just be used directly to track spine growth and elimination. And if you guys want to ever use this code or improve on it or use it for another project, here's my GitHub. Also, here's me currently running my code right now. And then in the meanwhile, while this runs, hope you guys enjoy it. And please feel free to ask questions. And thank you.